Hi, these are the lesson activities for differential equations, Math 204, section 1.9. First question, find a general solution to the differential equation by using an integrating factor. So the integrating factor is called mu of t, and we calculate it by doing e to the integral of g of t dt. So this is e to the integral, in this case 2 over t dt. All right, the antiderivative of 1 over t is ln t, and the 2 can come right out of the integral, so this is e to the 2 ln t. I'm not writing down a plus c because I only need one integrating factor. And then, so e to the 2 ln t, a little hint that I gave you just above here, is that you can rewrite that as e to the ln of t squared, right? Because when you raise a power to a power, you would multiply the exponents. So 2 times ln t gives you this. But then e to the ln t, exponentials and natural logs are inverses of each other, so e to the ln of t is just t. So this simplifies out nicely to just t squared. Okay, now we rewrite the differential equation. And we multiply both sides by the integrating factor. Distribute, so I have t squared times dy dt plus t squared over t reduces to just a t, so I have 2t times y. And then distribute over here, and I get t cubed minus t squared. Now, on the left, I have to recognize the product rule. One of my functions is y, because I have a y and a dy dt. And the other function is t squared, because I have t squared and its derivative. So this is like t squared times the derivative of y plus y times the derivative of t squared. So I'm going to rewrite this as, oh, that's just the derivative of t squared times y. Okay, now I integrate both sides. The integral of a derivative is just the function. So the antiderivative of the derivative of t squared times y is t squared times y. And the antiderivative of t cubed minus t squared would be t to the 4th over 4 minus t cubed over 3 plus c. And the only thing left to do is get that y by itself. So I divide both sides by t squared. So on the left, those cancel and you just get y. And on the right, we have to divide every term in the numerator by the t squared in the denominator. So we get 1/4 t squared minus 1/3 t plus c over t squared. Okay, number 2. Consider a pond that has an initial volume of 10,000 cubic meters. Suppose that at time 0, the water in the pond is clean, and that the pond has 2 streams flowing into it, A and B, and 1 stream flowing out, stream C. Okay, so we've got 2 streams flowing in, A and B, 1 stream flowing out at C. It has an initial volume of 10,000, and it starts out clean. Now we suppose 500 cubic meters per day of water flow into the pond from stream A. So 500 cubic meters per day go in through stream A. And 750 go in from stream B. So 750 cubic meters per day. And 1,250 cubic meters flow out via stream C. 1,250 cubic meters per day. Okay, at time t equals 0, the water flowing into the pond from stream A becomes contaminated with road salt at a concentration of 5 kilograms per 1,000 cubic meters. So I'll write that up here. 5 kilograms per 1,000 cubic meters going into stream A. Water in the pond is well mixed, so the concentration of salt at any given time is constant. And to make matters worse, suppose also that at time t equals 0, someone begins dumping trash into the pond at a rate of 50 cubic meters per day. So trash in at 50 cubic meters per day. Okay. The trash settles to the bottom of the pond, reducing the volume of the pond by 50 cubic meters per day. So the volume is now changing. And to adjust for the incoming trash, the rate that water flows out via stream C actually increases to 1,300 cubic meters per day. So the banks of the pond do not overflow. Okay, so we are going to set up a model to find S of t, the amount of salt in kilograms in the pond at time t. So S will be the amount of salt in the pond in kilograms at time t. And so ds dt is the rate of salt in rate of salt coming in minus the rate of salt going out, both measured in kilograms per day. Okay, so ds dt, the rate of salt in. So let's see, we have to know the concentration of the salt. So stream A, we have 5 kilograms per 1,000 cubic meters. And then, so that's the concentration of the salt. Then we have to know the rate at which the water is coming in, which is 500 cubic meters per 1 day. So you see cubic meters cancels and you get kilograms per day, which is what we were looking for, right? Because if we want to know the rate of change of salt, that's measured in kilograms per day. Okay, and then, so that's my rate of salt in, and then my rate of salt leaving is kilograms per cubic meter times cubic meters per day. Well, we know cubic meters per day is 1,300. And then I need to know the concentration of the salt leaving the pond. So the concentration is measured by how many total kilograms there are over the total volume. So the total kilograms of salt is the thing we're trying to model, right? It's S. S represents the amount of salt in the pond in kilograms. So on the top, I'm going to put an S here. And on the bottom, I want to put the volume of the pond in cubic meters. It was 10,000, but we're reducing it now by 50 cubic meters per day. So I need to do 10,000 minus 50 T to figure out the volume of water in the pond at time T. So there's my differential equation. The units really help because, again, the cubic meters cancel, and we get kilograms per day leaving the pond, the rate at which it's leaving the pond. Okay, so to simplify, 500 over 1,000 is a half, so I have 2.5. ds dt equals 2.5. And I'm not going to write the units just to make it look a little cleaner. Minus 26s over 200 minus t. Just simplified the fraction. If you write it out, you'll see you'll get there. Okay, now since at time t equals 0 the pond is clean, the initial condition is the amount of salt at time 0 is 0. And that's all we were asked to do, was come up with a model. So I've written the differential equation, given an initial condition, and I am done with this problem. They didn't ask me to solve it. Okay, find a general solution to the differential equation using an integrating factor. Hint, you'll need to use integration by parts twice. So this problem will be a great time to review integration by parts. So we'll do that in here too. I won't just tell you the answer. Okay, so my integrating factor, mu of t, is e to the integral of g of t dt. which is e to the negative 2 dt, which is e to the negative 2t. Multiply both sides of the original differential equation by the integrating factor. Okay, distribute, and I get e to the negative 2t times dy dt plus negative 2e to the negative 2t times y equals t squared, and e to the 2t times e to the negative 2t, like bases, you add the exponents, so that's just e to the 0, which is 1. So just t squared. Okay, now I have to recognize the product rule on the left. So it looks like my functions are e to the negative 2t and y. So this is d dt of y e to the negative 2t equals t squared. And then integrate both sides. Okay, so this is the antiderivative of the derivative of y e to the negative 2t is y e to the negative 2t equals the antiderivative of t squared is t cubed over 3 plus c. And then I just need to get the y by itself, so I divide both sides by e to the negative 2t. So these cancel, and we get y equals 1/3 t cubed e to the 2t plus ce to the 2t. I just divided the e to the negative 2t into both terms, and then I moved it to the numerator with a positive exponent. So there is my solution, and it looks like I was completely wrong in giving you this hint. You do not need to do integration by parts twice.